Okay, let's look at doing some examples in 5.4 using this fundamental theorem of calculus. So the big thing is to remember the difference in 4.8 when you were finding antiderivatives, that there were no limits of integration here. So in other words, if you had like x squared dx, then you use that rule that you add 1 to the exponent. Same thing happens down here. So you get this, and these are the ones you write the plus c, plus the constant, because you don't have this stuff here. So you're doing this first step from 4.8, you're doing that for 5.4. The only difference is now we're going to actually evaluate at within a certain interval. So if I have something like -2, 0, my interval of 2x plus 5 dx. Remembering that what you're doing, you're actually finding area underneath that function. And the fundamental theorem of calculus says you can do that by first finding the antiderivative. So the antiderivative of 2x, that's to the first power, so I would add 1. And then the antiderivative of 5 is 5x. So that gives me 2x squared over 2 plus 5x. Or just simply x squared plus 5x. Now here you don't do the plus c because I actually have this interval I'm going to evaluate. So you'll see this normally written like this from -2 to 0. And all that means you do is this is the part of the fundamental theorem of calculus that says f of b minus f of a, which just means plug in your b into your function and then plug your a into your function. So in other words, I'm going to plug in 0. So I'm going to have 0 squared plus 5 times 0. That's this part. Minus, in here I'm going to plug in -2. So -2 squared plus 5 times -2. And that's, of course, going to give me 0 minus 4 minus 10, which is going to give me a -6, or just simply 6. And that's the area. If I drew the graph, that's the area underneath that graph in the interval from -2 to 0. Alright, so if I want to find the area from 0 to 1, x squared plus square root of x dx. Well, I go through the same steps. So first I find the antiderivative. So let's kind of get faster at these. Remember what you're doing is you're adding 1 to the exponent, and then what I remember is the denominator is just the same thing. So that becomes x to the 3rd over 3. This piece here is the same thing as x to the 1/2 power. So we'll write that one in a few more steps. So that's x to the 1/2 plus 1. And the bottom will be 1/2 plus 1. So we have x to the 3rd over 3. We have x, if I change 1 to 2 over 2, that'll be 3 halves over 3 halves, which is x to the 3rd over 3. This, I can bring the 2 up to the top. So plus 2/3 x to the 3 halves. And this is what we're evaluating from 0 to 1. So once you get the antiderivative, then you just plug these values into your function and subtract them. So let's plug 1 in. So I'm going to have 1 cubed over 3 plus 2/3 times 1 to the 3/2 power. That's the first one. That's my f of b minus my f of a, which is plugging in 0. And these aren't always going to zero out, so that's why I'm going to the trouble to write these. But as you can see, this piece, like the one before, is just going to cancel out and be 0. And so all I have is this, which is simply 1/3 plus 2/3, or the area of 1. Continuing right along, if I have the area from 0 to pi over 4, tangent squared x dx. Well, the problem is I cannot find the antiderivative in my table, my little cheat sheet, formula sheet for tangent squared x. But somewhere in a bad dream, right, I remember this identity that said the tangent squared has this identity of secant squared x minus 1, and the secant squared is in that table. So I rewrite this as 0 to pi over 4 of secant squared x minus 1 dx. So now I look in my table and I find the antiderivative of secant squared is tangent. And of course the antiderivative of x would, of 1 would be x. I evaluate it from 0 to pi over 4, which just simply means I plug in pi over 4 for x, pi over 4 for x, minus tangent of plug in 0. That goes away because tangent of 0 is 0. Tangent of pi over 4 is 1, so I get 1 minus pi over 4, or about 0.2146. Okay, if I want to find from 0 to ln of 2, natural log of 2, of e to the 3x dx. Well, again, looking at my little cheat sheet from 4.8 of my antiderivatives, I see that the antiderivative of e to the anything is 1 over the anything derivative. Okay, so 3x would just be 3. And then the e to the anything stays the same. And now I just simply plug in, evaluate it at those values. So I can factor out a 1/3, meaning now I'll just plug in 3 times ln of 2 minus 3 times 0. I get 1/3. Remember, this whole e thing cancels out the ln, and the 2 comes down to be the base. So this then becomes 2 to the 3rd power, because we still have that 3 up there. This, of course, is e to the 0, which is 1. So I get 1/3, 8 minus 1, or 7/3, or approximately 2.33. So as you can see, all of these, the big thing is to understand how to take antiderivatives, which again is 4.8. That's why I mentioned you need to know 4.8 to be able to do 5.4. Okay, if I want to find the total area from 0 to 2 pi of sine of x dx, well, I just do what I've been doing. I look at my sheet and I see that the antiderivative is cosine, which would make sense because the derivative of cosine is sine minus sine, and so I tack on that negative so I get a positive sign, and I do this from 0 to 2 pi. So I plug in 2 pi minus a minus cosine of 0, and the cosine of 2 pi is 1, and a negative of course gives me a positive, and the cosine of 0 is 1. So what ends up happening here is you have to be careful with these, is if you look at this graph, what happened is this area and this area, they canceled out because this ends up being negative area that canceled out with this positive area. So what you have to do is get that value right there, and hopefully you know what it is from trig class, pre-calc class, that would be pi. If you didn't know what it was, then you just simply set your function equal to 0, and you solve for x. In other words, you find the x-intercept, and then you end up dividing this into two intervals. So now let's look at the interval from 0 to pi and pi to 2 pi. So now I'm going to have two different integrals here from 0 to pi, still sine x dx, but then also from pi to 2 pi sine x dx. Both of these, of course, the antiderivatives will be cosine, negative cosine. This is from 0 to pi. This is from pi to 2 pi. And so now when I plug these values in, so negative cosine of pi minus negative cosine of 0, this gives me 1 plus 1, which is 2. Negative cosine of 2 pi minus negative cosine of pi. That's very ugly, but that is a pi. This gives me negative 1 plus negative 1, which is negative 2. And you might say, but that's still going to cancel out. Well, what you end up doing is absolute valuing this. And so I take this area that I found, which was 2, this area that I found, and take the absolute value of it, and then that will give me my proper area. So all of these in 5.4 that you're doing, the big key, there's two big keys. One, you have to understand 4.8 on how to find antiderivatives. Well, all we did was shortcuts. We used that formula sheet that said this is how you do it. You do it with this formula sheet and these shortcuts. The other thing you have to be careful of is graph these first. Graph them, because that way you would have known right away that one area was going to cancel the other one out.